again. Welcome to the Academy. This is part of a video series on Cal 3 topics. This time we'll be talking about polar coordinates. So last time I was talking about double integrals, and we left off with an integral that was slightly difficult to perform in using the xy rectangular coordinates. And since the region we were integrating over was a circle, it's actually much easier to do in polar coordinates. So let's talk about how we can use polar coordinates. Just a quick review of polar coordinates. Basically, you have a point, instead of having x and y, you have r, the distance from the origin, and theta is the angle counterclockwise from this positive x-axis. And basically, in polar coordinates, you have some basic ways to convert to and from rectangular coordinates. You have here that x is r cosine of theta, and you can see that because the cosine is x over r. So x r cosine theta, and similarly y is r sine theta. Those are pretty important things to remember, as well as the Pythagorean theorem, x squared plus y squared equals r squared. So this is basically what you need to know for polar coordinates. So now, how do we put them into double integrals? And basically, what you see is whenever we change coordinate system, sometimes we don't want to use x and y, and we want to use some other coordinates. What you've got to do is you've got to find out another way to express your area component in the double integrals, which is in this case dA. So dA in Cartesian, you have it equal dx dy. It's Cartesian. So we want to see what is dA in polar. So let's go back to our original motivation. We have a region. We want to slice it into smaller regions, but if we're in polar coordinates, we're probably not going to have regions that are rectangular like in Cartesian, where you get easy stuff like dx times dy. We want to have something that's simpler. Polar, we have regions like this. A sort of circular slice. This is your delta A. So let's zoom in a little bit here, see what these regions look like. Kind of a slice here. And this is delta theta. This is a small change in the angle from this angle to this angle. And this is r, this is r1, and this is delta r. And this region, of course, is our area, delta A. So I want to find an approximation for this that will get progressively more accurate as these values get closer and closer to 0. We get smaller and smaller sections of area, smaller slices. So basically we want to consider this length right here. So the arc length, if this is a circular arc, the arc length, as we know, is r times the angle, in this case delta theta. this length here is r delta theta, and this one is r1 delta theta. But the two lengths, as these get smaller and smaller, these get closer and closer together, r1 will approach r. So these lengths will become approximately equal to each other. And as we get a smaller and smaller angle, the curvature here will get smaller and smaller. We get closer and closer to a straight line, approximately straight. Here, it will be approximately the same length on the other side. So it'll be sort of like a rectangle almost. It'll get closer to being a rectangle. And the rectangle's area, the area of the rectangle will just be the length of this times the length of this, which is just delta r times r delta theta. But of course, it's not exactly a rectangle, so this is just an approximation. But again, as we get smaller and smaller, it will be a better and better approximation until we finally get dA to the infinitesimal level equals r dr d theta. So basically, this is your area component in polar coordinates. And just a side note, units also make sense because angle is generally unitless. So you need two lengths multiplied together to get area. And so it can't just be dr d theta by itself, because that would just be length times a unitless quantity. So it would just be length, so you need another length. So the units work. That's a good way to make sure you're including the r, not just dr d theta. And so now let's see if we can solve that integral from last video. Basically, we're trying to do the function x squared plus y squared. The A and our region was the unit circle. So now we want to transform this into a double integral, or integral of integrals, but in polar coordinates. So x squared plus y squared, we don't want x squared and y squared anymore, because we're not going to be using x and y. Well, x squared plus y squared, this is just r squared. So that simplifies pretty easily. dA, as we know, is r dr d theta. Usually this is the order that we use. It's almost always going to be the angle, going to be the last thing we integrate over. In this case, it doesn't matter. You could do d theta dr, but this is generally always the order that you do it in. And so now we need to find the bounds. So this is our inner integral right here. So what does r go from? Well, r, we're going to make it go from 0 to 1 in all directions. So to keep theta constant, our r will just vary from 0 to 1 in all directions. There's a circle. And the angle, well, the angle just goes all the way around. It's from 0 to 2 pi. So now, as you can see, this is a much easier integral to evaluate. Well, integral from 0 to 1, r squared times r is r cubed. This is going to be, well, r cubed comes r to the 4th over 4, 0 to 1, d theta, and 0 to 2 pi. This becomes 1/4 minus 0/4, so that's 1/4, which is, well, 2 pi times 1/4. That's just pi over 2. And basically, if you had done the integral that we had set up last time, the very ugly looking one that was in Cartesian coordinates, you should have gotten pi over 2 as well, but as you can see, this way is much easier. So basically, polar coordinates greatly simplify calculations when dealing with circles and generally curved regions that can be expressed as functions of r. So basically the general form, just to give you the final general way of doing these. In general, we have some region that looks something like this.
Excuse me, teachers, for a brief announcement. Remember that we are having a faculty meeting at 2:35 in S100. Please make sure to be there on time so we can get you out on time. Thank you, and everybody have a great afternoon. We'll see you tomorrow.
Basically, if your region looks something like this, where you can have it as a region between 2 angles and between 2 curves that are, you can call R1 and R2. R is a function of theta. The polar curves, if you can express it like this, then you would transform your integral into, well, if this is f of x comma y, you would transform it into integral from theta 1 to theta 2, integral from r1 to r2, f of, this is going to be x, it's not x anymore, it becomes r cosine theta, r sine theta, r dr d theta. This is, so now everything is in terms of r and theta, and that's, dA becomes r dr theta. So this is how you would do it. So you can see there are several ways of solving double integrals, and that should be good enough for most regions. You can either do them in Cartesian or in polar, and there are some other ways to transform integrals that we might talk about in later videos. But for now, that was it for polar coordinates. Thanks for watching, and I'll see you in the next video.